Uh, so I'll introduce the speaker. Thanks, Luke, who who is giving the seminar from New Zealand in a very awkward time for him.
It's not
Um,
too bad. It's only 8:30 p.m. I'd be up anyway.
okay, anyway, thank you for agreeing to do that at this this time. So Luke will talk us about some linear algebra libraries that he has created. So yes, Luke, it's up. It's on you now.
All right. So first of all, I'm glowing red now because, as we said, it's 8:30 p.m. and the room that I'm in, if I turn the lights on, it will shine all over the screen and I can't see anything. So I'm using the light from the screen. I will stop glowing red shortly when I move on. And secondly, this is going to be pretty informal. It's going to be a little bit lecture-y, but mostly will be sort of live demonstration. I'll be jumping into the CAS chat terminal and showing you these functions, and we can see what they're doing. So I apologize if my typing is sloppy. I'm on a different keyboard than I'm used to, and I am not an accurate typer at the best of times anyway. So with those disclaimers out of the way, I'll get started. Also, if you have questions, please do ask. I'm a bit of a waffler by nature. And so, whilst I was hoping to go for about 45 minutes and then have plenty of time for questions, I suspect what will happen is I will go into details on lots of little things. And so, if you have questions, then stick your hand up either physically, or I know there's functionality here to do that, or post in the chat. And I'm sure myself and Constantino will keep an eye on that. Um, I would like to answer questions as we go. So, all right. So yes, we're going to be looking at stack contributed libraries. I'm assuming that everyone here has some amount of experience writing stack questions. I'm seeing the names and faces in the call. I think that that is true. Um, so really, what we'll be talking about is a specific set of libraries that I wrote 1 to 2 years ago, specifically for linear algebra. Um, but before I get too into that, I'll introduce myself. There we are. I'm no longer read. Forgive me if I just read from the slides for the first couple. I'm from Christchurch, New Zealand. I've always lived here. I studied mechanical engineering at the University of Canterbury, which is where I now work. I'm a senior tutor of digital learning development, which mostly means that I am the stack expert, as we sometimes call me. There's me, myself, and Speedy Jiang. We both work mostly on stack stuff. I'm in the mathematics and engineering mathematics, and he does statistics and data science. And when I'm not working on stack things, I am doing course management, tutorials, help sessions, just generally being around and helping the people who do the lecturing and design the courses and things. And outside of this work, I do a lot of music and theatre, and I have just finished playing Mercutio in a local season of Romeo and Juliet, which was very fun, but I am glad to have my evenings back, so that I can do things at respectable hours like 8:30 rather than going through till 10:30 or 11 p.m. on stage. Um, right. This seminar, it's going to be divided into three sections. The first and the third will both be very short, and most of the time I'll spend on that second point here. I'll talk a bit about contributed libraries, how you can use them in Stack, and sort of the quirks that come from doing them in Stack. Um, then we'll have a look at the specific libraries and look at a bunch of the functions, have a go at using them and just sort of very small toy problems to see some common applications, or at least how I like to use them. And then at the end, I'll try and have some salient reflections on contributed libraries more generally about the process of writing them and using them and et cetera, et cetera. I don't know how much I will have to say on that, but I'm sure I can think of something. Um, so, contributed libraries. If you've used any sort of coding language, for me it's Python, that has this sort of functionality, which I think is probably most of them, you will be used to this idea of inclusions. In Python, I'm used to starting everything with import NumPy. The contributed libraries in Stack give us the ability to do similar things. They let us use functions, copy text between questions very easily without us having to load everything in every time we start to work on a question. So they give us flexibility, but they avoid us needing to shove a whole bunch of stuff into the each session. Um, In Stack, there are two ways that we can include things. There are the include blocks in cast text. This is not something I'm going to be talking about very much here. Oh, I wanted a highlighter, not a pen. Highlighter. Um, these ones here are for putting things in the actual question body, and you can do all sorts of things here. I know at UC we mostly use include blocks inside JSX Graph, so that we can import some formatting that is common between all of our stuff. But I'm sure that there are myriad uses if you wanted to experiment with that. Most of what I will be talking about today will be in the question variables. Now, I'm sure there will be a more generic term. This is any time we're interacting with the Maxima terminal directly. So the question variables is the big one, but also feedback variables. And there are two key functions here. There's stack include and stack include contrib. Now, I'm going to go to this screen here. Hopefully everyone can see this web browser now, and this cast chat text. Great. I don't know if other people use this. I use this all the time. This is something where if you're wanting to try things out as you go along, you could do the same thing. If you just replace this URL with your local institution, I don't know if you need specific privileges or admin access. I somehow have them. So this is just going to be the cast chat screen, which lets me interact directly with the Maxima terminal without me needing to start and save a new question or anything. So if we start having a look at stack include, all this does is it goes to a URL. So we've got some URL that and takes the code or the text that it finds there and pastes it directly into your question variables. So in our case, if we go straight to the GitHub repository and we find, let's pick one. I'll start with rand matrix. I'll talk in a moment about where the structure of this. And I go to the raw code. Here is the code that is this particular library has. And so if I take this URL, copy paste straight into here, now I will have access to the functions in rand matrix. So in this case here, that means if I wanted to do something like generate a random matrix that is 3 by 4 with values between -5 and +5, then I can do that. And so if I get rid of this, if I comment this out, we will see that that is not, I no longer have access to this. So the function just behaves as an inert function now. Now, obviously, you can probably already tell this is highly cumbersome, right? This is pretty much everything we do if we're going through the native stack behavior. Oh yes, thank you, Chris. Chris has talked in the chat about how to get to this page. Pretty much anything we do in Stack, if we're using the contributed libraries, will have this prepended. Well, this will be the start of the URL in every case. So there's a nice helper function that is much easier to use, which is stack include contrib, and I can just go rand matrix dot mac. Now I can get rid of this first one, and my function will still work. As far as I understand, all that this contrib function is doing is prepending that URL to the front of this string here. I wanted to show stack include because that's a more powerful or more broadly useful tool. That's how I developed these libraries originally, was by using a stack include from my own GitHub clone of the stack repository. So I could save things there and test them in context. But in general, I think this contrib function is going to be more useful for sort of like casual use. I can definitely imagine a case in which an administrator would not want you to be using stack include and pulling code from wherever you like all over the web, but would be more comfortable using stack include contrib because this is directly pulling from the stack GitHub project. And so you can be a bit more confident of that it will be benign code, that it will be functional, that if something breaks, that it can be fixed. And so for the rest of today, I'll be using the stack include contrib and just picking out different libraries to have a closer look at. Excellent. So if we're happy using that, we should probably talk a little bit about the limitations of this. So because this is just a simple copy paste into code, it's not very smart. For example, you can't have inclusions that reference other inclusions. That caused me some headaches when I was writing these things because I have dependencies between the different things I've written. But you cannot include a script that then tries to include a separate script. You'd have to include both of them manually. And possibly even more significantly, does not allow you to sort of have live updating questions because it only does that copy into the code at the point that you compile the question. So that's when you save it or when you update stack and purge the cache and then run a question for the first time. If you are pulling code in from an external source and you update that code, you will need to resave all of the questions that use that code for them to get the new version. So it's convenient, but it's not exactly powerful, and it's not smart in that way of updating automatically or being able to cascade between lots of files. So those are kind of the traps here. But if you are just wanting access to using these functions that we'll spend most of the rest of this time talking, you can just use stack include contrib, and they will probably be pretty static. I did find some bugs in them whilst preparing for this talk. So there will probably be some small bugs, but they are hopefully few and far between. Great. Before we jump into the actual individual libraries, are there any questions so far about contributed libraries more generally? If not, let's move on then. So the structure of this, there are 7 libraries I'm going to talk about. The first of them is Rand Matrix, which we've already seen a little bit of. That one's a bit of a separate project. When I was writing these, it was because I had been given the green flag to write quizzes for our second year numerical linear algebra course for engineers. And so most of this was all part of one project. And I might talk more at the end of this. But I started poorly by thinking about all of the things I could possibly want when writing these questions and wrote all of these functions. And then I proceeded to use probably a third of them when actually writing the questions. But there's a lot of dependency between this linear algebra contrib file that the other ones all require. So I'll talk about those ones separately. But Rand Matrix was sort of a side project when I realized that I was copying the same randomization functions back and forth a whole lot, and I decided they deserved to be their own thing. So since it's standalone, it's a good place to start. Now, in here, the Rand Matrix file is divided into sort of 2 main families. We've got some that talk about the structure of the matrix, so randomly generating matrices with a certain structure or shape, and then there are a series that are used for properties. So I'll talk about these each, but you can read more about these. I am a little not super happy that I'm jumping back and forth between the slideshow, right? Like on the slide right now, you can see all of the things that I'm going to talk about, but we're going to lose that in a moment. So it might be worth mentioning briefly that you can get all sorts of information in the documentation, probably not surprising. If you go to the topics linear algebra section of the documentation, then each of these files that I'm about to talk about has its own page that's linked here. So I'll be showing examples, but if you want to look at the gory detail, you can go and look at each of these pages here, and they will have that stuff there. Thank you, Constantina. So let's look at Rand Matrix. So we've already seen this one here. Rand Matrix 3, 4, 5. The way to read this here is it's a 3x4 matrix, and it is going to be generated from values strictly between -5 and +5 inclusive. We can see that here with the matrix that we generated. All of these numbers are between -5 and 5. And we can do the same sort of thing with Rand Triu, Rand Trill, and Rand Diag. These names I took from Python and from NumPy. So these probably unsurprisingly make an upper triangular matrix, a lower triangular matrix, and a diagonal matrix using the same structure. We have a 3x4 matrix in each of these cases, picking values between -5 and +5. So if we run this, we should see we've got four matrices here. And as we expect, this one is upper triangular, this one is lower triangular, and this is diagonal. So nothing too surprising there. I actually don't use the rand matrix function very often. It's pretty rare that I want to just have some generic matrix. The only times I'm likely to be using this is when I'm asking students to do things like transpose a matrix or tell me what order a matrix is. The properties of these matrices are almost always going to be awful and not very helpful. But they felt like they were important functions to include. Um, each of these have variations. They all have list variants as one thing, where sometimes you don't want to have everything between -5 and 5, for example. Sometimes you would prefer to have from a specific list. So if I pick, say, maybe I want everything to be chosen from the digits 1, 2, and 3. So I'm going to specifically preclude zeros from being included. Then we can use the list version of this function, and it will pick from this list instead. So now we can see that the only zeros that we have when we run this code are in the sections of the matrix that we are ignoring, that we are setting to 0, and everything else is selected from 1, 2, and 3 exactly. This can be a nice way of, preventing zeros is the big one that I would use this for. And there is a no replacement variant as well in each of these. I know this is getting cumbersome with the names. I really couldn't think of a better thing to do. But at least it's consistent. We'll see here that actually most of these fail because I've only given three possible values, and I've said you are not allowed to use them with replacement. And so the only one that had only 3 spots to fill was the diagonal matrix. But we can, what do we want? Let's try the lower triangular one. Let's make this one, add some more options. We can fill it. Yeah, we can see that we've got 1, 2, 3, 1, 2, and 3 because of the options I gave. Again, these ones I don't tend to use quite so often. Rand diag from a list, it can be a bit more useful for perhaps eigenvector eigenvalue problems if you want to construct a diagonal matrix to then construct a matrix from. That could be useful. But those are how you use these functions. The possibly more interesting ones are the functions that look at particular properties. So, for example, we might use Rand invertible matrix. Now, since it's invertible, I don't need to tell it both rows and columns. It has to be square. So if we start with Rand invertible 3, it's going to construct a random matrix that is 3 by 3 and is invertible. This has a few other applications as well. Obviously, having an invertible matrix is nice sometimes, but you could also do things with this, like if I wanted to construct a linearly independent pair of vectors in R3, I could do something like, let's turn this into a list of column vectors, and then maybe I take the first 2 of these. Now I should have a list of 2 linearly independent vectors in R3. And I know that they're going to be linearly independent because they are columns of an invertible matrix. Even nicer, the one that I use even more often is Rand integer invertible. This one is particularly nice because it constructs an invertible matrix whose inverse is also filled with only integers. So the key example I can think of for that is if I say, let's take an integer invertible matrix, call it P. Let's do a rand diag from a list, make that a 3 by 3 matrix, and pick from, I don't know, 0, 1, 2, 3. And then we can construct another matrix, let's say M, which is P, D, P inverse. Now I have a matrix that I know will be constructed from only integers because it's made of matrices that are all themselves filled with only integers, with known simple eigenvectors and eigenvalues. And so sometimes you'll get that case. You'll get the case where you get diagonal matrices. But here we are. This is an integer matrix. And it's going to be different each time. But if I pull out its eigenvectors and eigenvalues, we'll see that they are going to be nice. We've got some matrix here that is randomly generated with nice values. If we wanted to make this more complex, there is an optional second argument to this rand integer invertible, which I think of as being the degree of complexity. So if I take, instead of just leaving it blank, I put 2 here. I'm expecting to get more complicated looking matrices with larger numbers. To peel back the curtain, what's really happening here with this rand integer invertible is I'm using the rand tri-u and rand tri-al functions to generate triangular matrices that have strictly, in this case, 1 or -1 as its diagonal values. We know that we are going to be constructing an invertible, that they will have determinants of 1 or -1, and so their product will also have a determinant of 1 or -1. And so when I change this value here, I'm just basically cranking up the value of the off-diagonal entries in those generator matrices. So if I even get up to something like 5, we're probably getting horrible, already getting big, big numbers that I don't want. But the principle is there. We can use this. The last thing that I might mention on this one is rand auth. In fact, let's go rand auth cols. Let's do a 4x3 with a this one here is that level of complexity that we were just talking about. This will randomly generate a matrix, or maybe that's a bit much. Let's just keep that as 1. A matrix with orthogonal columns. This can be really nice for sort of QR or least squares problems. And if we wanted to randomly generate an orthonormal basis, we could do the same thing I did before, like matrix to cols of this, and then we get a list, an orthonormal basis. And if I wanted to, I could map another function that we'll talk about later, scale nicely over this one. And this one here should make them all filled with integers. And now I have an orthogonal basis for this 3-dimensional subspace of R4 with all integer coefficients, all integer entries, which is a really nice starting point for generating a question. All right, I have waffled on and on about that. It's been 23 minutes. Are there any questions on rand matrix or any comments? If not, we'll keep on moving on. So yeah, it's probably worth mentioning for this rand matrix one. I highly recommend that I see this chat messages as well. Oh, thank you. Thank you for the comments. It's usually very important when using rand matrix to very aggressively trim your variance. Because we saw before, we got a random diagonal matrix that was sort of a trivial case, or sometimes you can get some absurd numbers popping up even with a low level of complexity. So these are a really nice starting point, but I urge you to not think of them as the ending point. It's good practice all the time, I think, to sort of check your variance quite closely. But this one really tests your ability to write a useful question note, I think, and then trim those down. To answer your question, Sam, so for these last ones on orthogonal columns and integer invertible, I think with orthocols, I am generating a random invertible matrix using the existing function and then just performing Gram-Schmidt on it and normalizing. So I'm definitely not like I'm starting with something that has a known form. So yeah, either in this case they're always triangular. There's products of triangular matrices. For rand auth cols, I'm just taking generating an orthogonal matrix and chopping off columns. Like if I tried to change this to 3, 4, rather than 4, 3, that's gonna break because it can't do that. You can't have 4 linearly independent columns in R3. This notation here, this is just what we chose as the baseline error message, basically. We don't get access to the error codes in the question variable. So if you ever get a null, that suggests that something's probably gone wrong with your inputs. Great. Okay, so let's have a look at the next set. So yeah, linear algebra contrib. This one's interesting. If you're using a version of Stack from before 4.9.0, you will need to include the file linear algebra contrib to be able to get access to any of this linear algebra stuff. But if you're using Stack 4.9.0 onwards, this is included by default. You don't need to do any inclusion. So the functions we talk about in here are available to everyone without needing to use include. Some of them are just very basal functions that we want to use all the time, and some of them are there are dependencies later on. So actually, this is one of the things that motivated me originally to write this stuff is student vector input. We do vector geometry very early at UC. The engineering students need it for their physics courses. And so we had a lot of questions in which we're very prescriptive about how students write their answer. So if a student doesn't know that we expect their answer to be in the form of some constant DC offset plus a linear combination of direction vectors, they can kind of infer a lot about their solution, what the answer should look like by the answer boxes that we give them. And I don't want to give first year students free access to typing matrix equations in. I think they're going to get very confused by the matrix notation. So I created these C and R functions. Let's have a look at this in here. So we don't need to include anything here, but we do need to type in, see if I remember that off the top of my head, stack linear algebra declare. This tells us that we are working in a linear algebra environment, and it activates the formatting for these C and R functions. And actually, let's do it up here. If I have some student input, maybe they've got some plane, or no, let's say a line in R3. It's going to look something like this. It's some R0 linear offset, like DC offset, and then a direction vector. And if I print this one out, it will display as a matrix equation. And so, or as a vector expression. So this appears in students' input in the validation. So as a student types this in, they'll get to see this normally, which is the big thing I wanted to do. It can handle all sorts of things. Like if you use a row vector instead of a column vector like this, it will actually display this, even though this is sort of a nonsense statement, right? It's happy to display a sum like this, because in the backgrounds, these are just inert functions that are displaying. Like if I print out what's going on, it reads them just purely as these unknown functions C and R. So if you want to do anything with these, you need to use this function vec convert. And so actually, yeah, if I do this here, this one looks like it has nothing's changed, and that's because it has. If we look at this here, we're going to see this is still R and C, and that's because these don't conform. If I change this to a C, we can add two column vectors, then we get a matrix now after we vec convert. In this case here, that'll be just the normal SA by itself is going to display it as a sum of vectors, but then if I vec convert it, then we get a single vector. And these can also handle things like dot products and all that. Like if I wanted to do SA versus vec convert SA, this should be able to figure out what I want. Yeah, great. It's given me a scalar. So you can use these just by using stack linear algebra declare true, and then vec convert to change it back. Also worth noting, there's a vec converted p predicate function. This tells you whether it was successful when it did its conversion. So if we go back to that example of me adding a row vector and a column vector, I'm going to try and convert it to matrix form, and it's going to fail because these don't conform, and this is going to, the vec converted p function is going to tell me that. So that's a useful check at the beginning of the PRT to make sure that the student's given you something at least vaguely sensible. You could probably do a bespoke validation function based on that if you needed to. So that's a whole system there that is, I find very useful for student input. But there is more in here. What are we looking for? Oh yeah, I won't go into detail about this. There's these predicate functions for vectors and matrices. Vec converted p is one of them. There's also rovec p and colvec p to check if something that is given is a row vector or a column vector. And we have a couple of functions, diag p and square p, that checks whether given matrix is diagonal or square. You can imagine those are useful for predicate functions further down in this library. Then there's some helper functions. We saw that function before, matrix to cols, that I used a couple of times to extract the columns of a matrix. There are a handful of those here as well. There's cols to matrix. There is make list of lists. They are basically just used to convert between various different canonical forms that we might want to use. I don't see them being particularly useful in sort of day-to-day usage, but you can again have a look through the actual code or through the documentation if you want to see what type of conversion functions we have there. I will draw special attention to these gems here. I like these two functions. I thought they should be in base stack, so I put them here. Scale nicely, we saw before that. Originally, I called it integerify. It basically takes, anytime you've got a vector whose direction is important but whose length is not, use scale nicely, because it replaces a vector with the shortest parallel vector that has all integer coefficients. So that was what I used when I was looking at that orthogonal basis. I generated an orthonormal basis and said, actually, I want this to have integers, so I used scale nicely. I mapped that over each of those vectors. And I keep finding more and more use cases of this. You can use scale nicely with a little bit of finagling to take matrices that have fractions in them and extract a fraction out the front. So you've got an integer matrix with a scaling coefficient there as well. I sometimes use it when writing plane equations. So if you've got like 2x plus 2y plus 2z equals 2, and you want to get rid of that factor of 2, you can, with a little bit of finagling again, you can scale everything down to single, like to the ones in that particular case. But yes, this is just a generic function that you can use at any point if you've got 4.9.0 or later. And then matsolve mostly comes from the fact that I originally learned to code in MATLAB, and I was surprised that I couldn't do an a\b to solve for x when I was using maxima. And there is the invert function. If a is invertible, you can use that to find your solution. And we even have, I'll actually point this one out in particular. We even have pinv. Let's say we have A, which is some matrix 1, 1, 2, 2. So it's a singular matrix. And then let's say we have some B that is, let's put it not in the column space. Then if we wanted AX equals B, forgive my bad typesetting here, then we would have X equals, we obviously can't do invert A times B. That's not going to work because A is singular. But we can use the pinv function, the pseudo-inverse, that'll give us a least squares solution to this problem. But neither of those options, this one here is not native. There is the more Penrose pseudo-inverse function, which has too many letters in it, and I never remember where the underscores are. So in this file, I renamed it to pinv. None of these cases let us deal with general solutions. So instead, there is now matsolve AB. Now, in this case, it will still fail because there is no solution to this. It's inconsistent. But if I then say true, this third optional argument tells me that I want to look for least squares solutions. It will give me a least squares solution, and it will give me the general least squares solution in this case. We get rid of those percentages, stacks, percent. Ooh. Then we get some nice answer here. And if we don't want to look for least squares solutions, but we did have some answer that is in the column space of the singular matrix, we will get a general solution. So matsolve is a nice way of probably mostly for creating model answers, but it sort of patches that gap, I think. So the C and R notation, I'm seeing your comment there, Mark. That one is, we have to activate that one directly because it's likely that C and R are being used in existing questions. So we couldn't just load that one in as or even if they're not being used in existing questions, someone may want to use C for another reason. And so you have to activate that one for the formatting purpose. But all of these other ones are there. And so what input can it handle? Also matrix equations. So what is actually happening here? It specifically needs a matrix and a vector, and a column vector specifically as an input, because all I'm doing here is converting it into a system of linear equations with dummy variables, and then running the linsolve function on it and converting the answer into a sensible input. So it's really just the existing maxima linsolve function, with some window dressing to accept different inputs. And then if you want the least squares functionality, then all I'm doing is solving the normal equations. So if you, for example, had a matrix B, I don't think that would work. I haven't actually tried it. That was not the intended use case. If you want to do some changes to that, I encourage you to. That's the nice thing about these is they are quite low stakes to just jump in and try and make something work, because they're not core stack. So long as the existing functionality is preserved, you're safe. Cool. Are there any other questions or comments on these ones?
I think there is one more comment.
I think I've answered both of these ones. So yeah, because you do need to activate the C and R notation, and then that's the inputs that we're allowed for matsolve. Neat. So what's my time? 40 minutes in or 38 minutes in. That's not too bad actually. Because some of these later ones I'm going to go through in less detail. Matrix has got quite a lot in it here. This one I view as being my scalpel, using which from which I cut up my matrices, perform surgery on them, as well as some useful predicate functions and some formatting functions. So let's look at these formatting functions first, because I think that'll be one that will interest people as well. So the first of these is org. So I've got to remember to include these ones, stack include contrib. What am I doing? Matrix.mac. Now, if I had some matrix equation, let's say my favorite matrix here, and we got B, some right-hand side vector, like this, and I want to display the system of equations AX equals B as an augmented matrix. What I can do is I can use org on, now it's a little clumsy, I do have to construct a matrix. Let's do it up here. Let's call this a variable AB. Use add col on A and B. All that's doing is appending the column B to the right-hand side of the matrix A. But then if I display org of this, it will show as an augmented matrix, which is much nicer than having to manually type out an augmented matrix, in my opinion. This is also, it respects the preferred character. So if I change the brackets to round brackets, for example, then this will display with round brackets. Or if those are probably the two that you want. Presumably curly brace would work as well. Yeah, great. So it respects that. All it is really doing behind the scenes is constructing two matrices side by side, where one of them has the appropriate opening bracket, the other has the appropriate closing bracket, and in between we chuck a vertical bar there. So it's if I show the actual output of this, oh no, org matrix it's a tech put thing. But I find this one a really nice way to display these. The thing to be aware of is what we can do is we could say AB is org of this, and then we could just display AB directly. But you can't do matrix algebra on an org matrix. So if I wanted to do like a row operation, I would need to use the dorg function, and then it would become a matrix again. So this one here will just be a matrix without that extra bar in it. And then I can do all of the stuff I want and then org it again. So this is a nice one for simplifying your display. Another one that I like, and now this one I'm actually going to have to copy paste some stuff in. is the disp equations function. This one here, I got fed up with aligning all of my equations, especially when it comes to some things having like negative coefficients, some things having zero coefficients, etc., etc. So I wrote a bulky function that does all of it for me. Now, I think I copied this into my notes, which you can see because I decided to do it this way. Yeah, so if I take this one here that I'm copying in is just it is the unit test inside GitHub that shows this, but I can just display a system of equations nicely aligned with variables where they're supposed to be and gaps where I want them to be without having to do any LaTeX formatting myself. This takes in a list of equations and then a list of variables, and that is all you need. It should do everything itself. Now, this has been one of the ones that's had the most bugs in it because it tries to do so much. But I think I'm pretty happy with this one by now. Yeah, this is a useful thing. It's a bit of an obtuse example here because I've specifically constructed this system of equations to kind of have everything that could go wrong go wrong. But hopefully that is a useful thing. I find that useful. There is also a variant of this one called matdisp equations. Matdisp equations, which does the same thing but uses matrix input. So again, I can copy paste from here. If I've got these two matrices A and B, this A and B is the matrix that we see here. So if I actually can get rid of this one because we're going to see it twice. If I do matdisp equations of A, B, and then my variables, what are they? X, Y, Z, and W. Then I think that's done the right formatting here. Oh, I've got to put it in the LaTeX environment. It should show me my equations like that. So just to make that abundantly clear, we have A and B as a matrix and a vector. And then I can display it as a system of equations. Hopefully that one is useful as well. I like that it also, if I've got a row of zeros, it will display that appropriately as well. That was the biggest headache that I solved most recently. So those are the display functions. Are there questions about that one? I think that they are something you kind of got to play around with yourself to figure out how they work, but hopefully it's reasonably self-explanatory. All right. What else was there in here? Oh yes, performing surgery on matrices. Oh, let's go to the nicer one, bigger one here. So from before we have returning trial, triu, and not diag this time because diag was already taken. That's another function that already exists. But so diagonal, these ones will do the equivalent of what the NumPy functions do. It will extract the lower, upper, or diagonal part of your matrix, and basically by setting everything else to zero. So if we wanted, I mean, we can try these very quickly. Let's include rand matrix. I needed the matrix there as well. Actually, we've got an A and a B. Let's just use those. If we take triu of A, we'll get that upper triangle. Yeah. So we've deleted all of the stuff below the diagonal. And you can imagine similar for trill and diagonal. Then we have these set row mx, set col mx, and set diag mx. Native maxima has set element mx or set l mx. And I thought it was a little silly that we didn't have the sort of equivalent functions for changing rows, columns, and diagonals. The notation of these are the same as the element function, set element x, where you tell it what you want the row to be, which row you want it, and then the matrix that you're wanting to do, that you're wanting to update. I mean, set row matrix is not super useful because you can just index it directly. You can change a row directly, but set column is a bit more useful. And set diag is nice as well. This one here, you give a list of the things you want on the diagonal, the matrix you want to do it to, and then an optional argument k, which can be which just needs to be an integer, defaults to 0 and tells you which diagonal. So if you did lm1, it will populate the first super diagonal above the main diagonal, and lm0 would just do the main diagonal, etc. Those ones, so you could use that to construct a tri-diagonal matrix or something. I mean, when I was writing rand matrix, I did think that you could do so many, right? You could never stop creating functions to randomize in certain forms. At the end of the day, I decided that some of them should belong here. And then diag entries and diag matrix like. Diag entries will extract the diagonal of a matrix as a list. And then diag matrix like, if you give it a what am I doing here? I think you give it, I don't even remember the formatting for this one. Diag matrix like lets you construct a matrix of a certain size, m by n. And in this case, I need to check that one there, whether you give it a list or whether you're telling it what matrix you're wanting it to be like. I clearly don't use it often enough, and I don't want to trawl through the code to figure that one out. I think this one appeared when I was making my SVD function, and I wanted to be able to resize a matrix and keep the diagonal the same. So not a very common one. Then lastly, we've got these predicate functions, which I will talk a little bit more about. No surprises, we have a trill-p and a tri-up are our matrices in lower or upper triangular. We've already seen diag-p, that was one of the predicate functions in the previous slide. And then there is sim-p to check whether something is symmetric. Again, some of these are very easy to do. Symmetric, is it equal to its transpose? It's nice to have a predicate function for it. The more interesting ones here, I think, refp, that's one of my favorites. This one is row echelon form as a predicate. So if we go to, let's play around with this one. Let's keep using our A. No, let's randomly generate a matrix. Let's go rand matrix. Let's go 3 by 5, and let's have big numbers. And so have a look at our A. So obviously this is not in row echelon form, but the stack has a number of functions that can let us put things in row echelon form. We've got RREF. I think this one's a stack native one, not a maxima native one. But we also have as other options echelon A and triangularize A, which I think are both maxima native. So yeah, our random matrix has an awful RREF, but sometimes you want to check whether a student has appropriately got it in row echelon form, but you don't care about them going all the way to row reduced echelon form. And so obviously if you're not going all the way to RREF, then you have a whole set of different possible valid solutions. And so this function refp would return true for all of these forms here. They're all in row echelon form, even if they're not all reduced. Now, I know that row echelon form does not have an agreed upon definition. Some people insist on the leading coefficients being 1 for it to be truly an echelon form, and other people do not. And so there is an optional argument here. If I run refp on all of these with my optional argument true, we will see that if we set this to true, then this will require those pivots to be normalized to 1. I want true. So if I run this, it's going to take its time. In this case here, the row reduced form and the echelon form have both returned true. But this one, even though by some definitions it's in row echelon form, because it doesn't have leading coefficients of 1, some would disagree, and so it rejects it. I see that there's some questions. Okay, so that's all good. So I find this one useful for checking for whether something is correct when there are infinite possible solutions. The other ones that we could look at are, I mean, there's diagonalizable P, invertible P. They do what you think. They check whether a given matrix is diagonalizable or invertible. And then we have a few functions. Orth matrix P has the student given an orthogonal matrix. And then I think there are two that are like orthogonal columns and orthonormal columns for the sort of weaker versions. Has the student given a matrix with orthogonal columns? Again, you can check that in the documentation if you want to look at any of those. I think they're reasonably self-explanatory. So that is the matrix library. Are there any questions or comments on that one? No. All right. From here, I think we speed up a little bit. They get a bit more self-explanatory. This one here is eigenlib. There are actually quite a few very useful functions natively in Maxima or in some of Maxima's packages that help you deal with eigenvector eigenvalue problems, but they never had the type of function that I wanted. So first of all, there are a couple of predicate functions here that let us check whether a given vector or a given scalar are eigenvectors or eigenvalues of a matrix. There is also an optional argument in here to check whether a given vector is an eigenvector that corresponds with a specific eigenvalue. So to check this one I think is worth having a quick look at. If we do eigenlib, and let's go back to my favorite matrix. This is my favorite matrix because it looks at first, it feels like there's no reason that this should be singular, but it is. So I use this one as an example all the time. So if I want to know, let's say, eigenvalue P 0a, then we find that yes, 0 is indeed an eigenvalue of A, which is what we would expect. But then if I want to ask, is 0 an eigenvalue of A that corresponds with the eigenvector 1, 1, 1? Then we find false. It is an eigenvalue, but it is not the correct eigenvalue that we're looking for. Similarly, you could do things like eigenvector P, where in this case we now want, let's take something, well, let's take our 1, 1, 1. I don't believe that one is an eigenvector from memory, so we should get false. Oh, did I miss a bracket? No, but we're good. But I do think 1 minus 2, 1 is. So we find that yes, 1 minus 2, 1 is an eigenvector. And then if I ask, is that the eigenvector corresponding with the eigenvalue 0? I get yes, it is. Is it an eigenvector corresponding with eigenvalue 1? We should say no. It is not I don't think 1 is an eigenvalue of this matrix. So this kind of gave me the flexibility I wanted. A lot of the time, just knowing what the eigenvectors and eigenvalues of a matrix was not helpful. This one is very useful for marking student answers, I find. We can also, rather than checking whether something is, we can extract the relevant eigenvector or eigenvalue. If you want to know all of the eigenvectors and eigenvalues, then we've already got the eigenvectors function that Maxima has natively. So we don't need anything new there, but getting a specific eigenvector or eigenvalue is quite nice. So if we go back to our example with A and we want to get the eigenvector associated, I never remember the order of these inputs, and they're not consistent. I apologize for that. Get the eigenvector Lm. So I want the eigenvector associated with the eigenvalue of 0. And it extracts the eigenvector we want. And you can see it's a list of vectors here, because obviously we could have an eigenspace with greater dimensions than 1. And so if we did that, we would get a list. If I pick something that's not an eigenvalue, then I believe we get an empty list because there are no eigenvalues no eigenvectors corresponding to that eigenvalue because it's not an eigenvalue. I think I did save a matrix somewhere to show here. Yeah. So that we can see what happens if we get if we change A to this new matrix and we get the eigenvector associated with 1, then we find that this matrix has a repeated eigenvalue and a two-dimensional eigenspace. We get the list. This also has an optional argument. If you put true as a third argument, it will orthonormalize your basis. You'll get an orthonormal basis for your eigenspace, which could be useful. It felt like something that might be nice to have at times. I don't use this functionality, I don't think. I would usually start with the orthogonal basis and work backwards. So those ones are nice. Was there anything else going on here? Oh, yeah, and then the multiplicities of these. Go back to the Zoom one. the algebraic and geometric multiplicities of a given eigenvalue. That is just a nice thing to know without having to go through the process of extracting the whole the all of the eigenvectors and eigenvalues and counting. Um, so that one was probably mostly useful. I think I used that one in a question where I have a bunch of random matrices, some of which are defective and some of which are not, and ask students to identify the multiplicities or whether it is defective, etc. So if I've got a question that has some things that are defective and others are not, this can be a useful way of generating the marking code. That's eigenlib. It's called eigenlib because eigen already exists as a name. That's the name of the native maxima function. Right, I'm going to keep moving on. Again, please just ask questions if you have them. Vector spaces. This one here does a few different things. There's some predicate functions. These ones I use a lot. These are really nice. So row equiv p and col equiv p. Check whether two given matrices are row equivalent or column equivalent, as you probably guessed. This one is nice for questions where you want the students to do some level of row reduction, but maybe you don't care whether it is well, no. If I wanted to know whether students have done some row reduction appropriately, I'd use the refp predicate function that we looked at before to check, have they given me a matrix in row echelon form? And then I would use this row equiv p function to check that our two matrices are row equivalent. And that should be sufficient to determine whether they've got a correct answer. It checks the form and checks the property of it. You could do a similar thing with col equiv p if you were doing some sort of QR function. And also handle Jordan canonical forms or kernel with respect to p. It's a nonlinear polynomial. Sorry, Raphael, which one was that? Was that talking about
So if it maybe, or if somewhere in the linear algebra lib there's an adaptation of the eigenlib, which might be available for, I don't know, Jordan canonical forms, or when you have something like a matrix 2 by 2 real valued matrix without real eigenvalues.
Oh,
But
sure.
also you
So I know that we do have stuff for Jordan normal form. This is the next slide ahead. There are some native functions that give you Jordan normal form, Jordan normal form. And there is one that I've written that sort of stitches that together and gives you the constituent bits. That one is, yeah, mostly maxima native. And I know that I believe the way that I check certain things in here is by looking at the Jordan normal form. I can't remember exactly how those ones work. I'm not sure if that answers your question.
Oh, for now it's fine. So then I check up what the maxima native functions do, but
Yeah, cool.
and then have to
Great.
work with them.
Yeah. But yes, so we have these equivalent functions, row equiv and col equiv for matrices, and then subspace equiv, which is quite nice. That one works if you give it a list of vectors. Then you can check whether the span of these two different lists of vectors are equivalent. There's also lin int px, checks whether a particular a given list of vectors is linearly independent. I think that also accepts a matrix input. If you take lin int p of a matrix, it checks whether it is has full column rank. And you can imagine that combining subspace equiv and lin int p, you can check whether a student has given a valid basis for a subspace that you have defined. This is one I use all the time in our second year linear algebra course when we're asking students to find column spaces and null spaces and stuff all the time. I check whether the student's answer has the same span as my answer, and I check that it's linearly independent. And if those two things are satisfied, they have given a correct answer. It is worth noting that it's not always great at dealing with redundancies if you ask students to give their answer as a set, because if the student gives the same vector twice, that is not a basis, but maxima will annihilate the duplicate before it marks if you don't go carefully through and convert to a list with simplification off and things like that. But I think that's an edge case. I don't think there are many students who would give you the exact same vector twice, and as a way of circumventing good marking. Yeah, these next functions are, I don't actually use them too often. Orthogonalize and normalize do what they sound like. If you give them a basis, they will orthogonalize or normalize that basis. This optional argument SP means you can give a different scalar product. If that's left blank, it will default to the standard inner product. But you could give a different dot product and it would be fine there, which I think these are mostly just wrapper, or the orthogonalize is mostly just a wrapper for the Graham-Schmidt function. Presumably also over R/C. We don't do CN stuff in my numerical linear algebra course. So where I thought to do it, I made it work over complex numbers. So rather than choosing to transpose things, I would try and take Hermitians, etc. I haven't tested that much. So that is actually worth being careful about. I have done all of my stuff over real matrices with real scalars because that's what I use. I have not gone out of my way to check that it works for complex. It will probably be very minimal changes needed to make it work for complex if needed. Yeah. That's a very good comment. Yes. The remove dep and basisify functions, remove dependence. This, if you give it a set of vectors, it will from left to right remove the dependent vectors, leaving a minimal a basis. This one I don't think is super useful for, I haven't really used that one because I don't generate bases that have extra vectors, but that could be useful for generating feedback for students, saying here is a better answer or something like that. And basisify does the opposite. It expands a given basis up to the full Rn. So if you've this one I actually made originally for SVD functions again. If you create if you have some basis that spans some subspace of Rn and you would like to extend it to cover all of Rn, then basisify will do that. Oh, sure. Yeah, I have actually been doing some work in linear algebra with what is it? I'm an engineer rather than a mathematician over binary codes recently, and that required a bit more finagling. Yeah, I was doing things like converting matrices to lists of lists, mapping a mod function over it, and then reconstructing matrices. There is not support for that in this one here. I had to do some actual work for that. That could be a good thing it could be a good second project to do. Great. And then lastly on this one, we've got a few extra, mostly patch-up functions like column space and null space already exist as functions. And because of that, I always forget that row space and the co-kernel don't exist. So I added them here because I would like them to exist even if I don't use them quite so often. I don't like the name null T space, but I couldn't think of a better one because null space is not called kernel. It's called null space in Maxim. Projection matrix will construct a matrix that projects onto the column space of a matrix. I don't know how useful that is, but again, it felt like something that could be useful for assessing like least squares problems and stuff, or providing feedback. And then unit vec p checks whether a given vector is a unit vector. That one I believe does work in CN. I think that's one of the ones where I actually remembered to check. I'm not super confident though. All right. I know the last ones I'm not wanting to talk about much, so I'll move on and then we can come back for questions as they appear. So matrix factorizations, this is included because it felt wrong to not, but I don't use it. Again, we probably all know that best practice when generating questions like this is to start with a solution that you want them to work towards and then generate the problem from that to ensure that the numbers sort of work out nicely. if you are going to generate a random matrix and then find its SVD, you're probably going to have a bad time. So I don't know how useful this is generally, but it could be nice for work solutions. It could be nice to as a for something that is not the central part of the question, but that is useful for students to see or something. This includes QR factorization. It packages diagonalization and Jordan canonical form into some more useful functions that actually give you the modal matrix as well as the canonical form. And there's some SVD functions here. SVD red that's reduced, so it produces the sigma that is invertible, and the U and V that have orthonormal columns but are not necessarily orthogonal themselves. And then just the SVD function will expand that to a full SVD with orthogonal U and V. The problem with this, and I think this is partly why Maxima doesn't have all of those doesn't have these tools natively, is I don't know how useful a reduced SVD is when you're working symbolically. Because even if you're dealing with small, like 2x2, 3x3 matrices, the SVD that you get out the other side is awful most of the time. You have to be very careful when constructing these problems to make sure that you actually get workable numbers by hand. If you're wanting to do work with SVD, you would do it numerically, and Maxima is not built for that. In fact, I sometimes had to really, really twist its arm to make it even convert things to floats that I thought should be very easy to convert to floats, especially when complex numbers start showing up. So I'm sure there are use cases for this. I have not found many of them myself, because when I get students to work with SVDs, I put them in CodeRunner and doing Python. Yes. So yeah, I don't have too much to say on matrix factorizations. It's there for completeness rather than because I think it's entirely that useful on a day-to-day basis. And then the last one I also won't talk about in great detail because I think it's a little clumsy. I've done my best with this, but I think it's tricky. This is the vector geometry. So this is going all the way back to the start, looking at affine subspaces, where I frequently want students to give me answers in a form like this, R0 plus like some DC offset and a linear combination of direction vectors. This library provides us with some functions to check how things are to work with these more naturally. Oh yes, SVD and exams with no calculators. Yeah, I have. This is one of those ones where trimming the variance after randomly generating a bunch of stuff has been my friend in our course. Anyway, vector geometry. So this is one I do want to have a proper look at. Where are we here? Vector geometry. When I load one of these libraries, that automatically runs that stack linear algebra declare function. So even though I haven't written it here, I can still use C and R notation. So that's if you're importing one of these libraries, you can skip that step. But if I have a student give me, let's say they are trying to describe some plane, it's going to be C123 plus T times 234 plus S times 111, something like that. And so we've got the student's answer. I would like to be able to check whether or not this answer is equivalent to the answer that I'm looking at, equivalent to my correct answer, because obviously you could do any linear combination of those direction vectors. You could choose any point on the plane and it would be valid. So there's some convenience functions here. There's one function called vector parametric parts that takes that answer and breaks it into its constituent bits so that we can then work with them. Let's call this S parts. This is of the form, it's a list where the first element of the list is the constant DC offset they've given us. Then it gives me their direction vectors as a list and the corresponding parameters that are used to scale those direction vectors. From here, we can do some things like if I wanted to display their answer back to them to show them how I've interpreted it, I can use the function vector parametric display, I believe is what I've called it, on the parts. And that should display it back to me nicely. Yep. And particularly it does it in the form that I want with the offset at the start and then the set of direction vectors in the order that I've received the variables, the parameters. So that can be useful for your answer has been interpreted as. Yes, Mark, there is functionality for that. So if the student, let's do exactly that. So I actually pushed a bug fix to this particular display question today. So it might look wrong. We'll see. What have you said? C. So if the student answer is something like this, nope, I wanted to copy. Is it going to let me do it now? It's not. Okay, I'll just copy it manually. C1 plus S times 2 to 2. It might break the vector parametric display thing for now, but yeah. So it's understood what we wanted here. It's understood that we want 1, 2, 2 as our set of constants, and then it's extracted the direction vector. I believe there's even capacity. I need to actually go and look through the actual code for this to check. To declare certain things are constants, and therefore are not. What am I doing here? I'm looking for. Yeah, there's an optional argument to exclude certain parameters. So if you were all dependent on some answer, some unknown constant k, you could declare that k is not a parameter in this particular case, and then it would cope with that fine. Yeah, so we were displaying this. Then actually, this looks like this was where the bug was coming up before. So it looks like my pull request has been accepted and the bug has been patched already, which is nice. There was an extra plus sign here earlier today. You can also do things like check whether the student answer, what do we have? There's check point and affine space, I think. No, it's just called point in affine space P. And then you could take the student's answer. So maybe we take the first part of S parts, and then maybe we have T parts because we've got a model answer. We will then check whether the student's DC offset is in our plane, is in our subspace, or affine space. And so that's one check. And then you could also check, what is it? Vector in space, P. And then the way I would approach this is I would take each of my direction vectors. So I might do my first of the second part of T parts. Check, is that in the student's answer? If people want after this, I can go and find a question that uses some of this and we can have a closer look with actual examples in here. But the point of this here is that we can interpret a student answer into its relevant parts, and then we can check whether those parts can construct a valid plane or a valid subspace that we want, whether their answer is correct. And so all of it wordy, which is why I don't really love this one here. I often find that figuring out the best way to set up my marking code takes about as much time as just doing it manually each time. So I'm not convinced that this has come out the best way. And if people have suggestions for how to streamline it, please let me know. Part of it might just be better names for functions, because these ones are all clumsy. And with that, I believe that's the last of the libraries I was going to be looking at. Yeah, I'm very aware that it's been an hour and 15 minutes. Are there any questions or concerns or comments about any of the things that we've looked at in these different libraries before I start to reflect a bit more about the process of writing these and the usefulness of them? Excellent. It's also worth me noting, I forgot to say before, big thanks to Gail Gosang. I'm actually not sure if I'm pronouncing his name correctly. He did a lot of work on this just before we published. So I wrote most of this through late 2024, early 2025. No, late 2023, early 2024. Regardless, just before we published, he put a lot of work into improving some of these functions, particularly in the vector spaces stuff. And so thank you to him. He's noted in the files themselves, but that was much appreciated. And so that's a good segue into the reflections on this stuff here. So as I say, when I wrote these, I took what I think was a bad approach, which was I looked for possible problems that might arise, and I tried to solve them ahead of time. And that's where I get things like these SVD functions that I never have used, really, because I thought that I might want to use them. When I was first introduced to these contributed libraries as a concept, it was because I helped out with the vector calculus contributed library, which has some divergence, gradient, curl, Laplacian functions, perhaps. And what I remember Chris saying was, if you ever find yourself copying code between a lot of questions, we should just make that part of stack. And so some things, if you do that, it should just become part of core stacks. But other things like this are better put into a contributed library like this, so that not only can you avoid copy pasting code between questions all the time, but everyone else can avoid that too. Since I started from that perspective of let's try and solve all of my problems in advance, I had too much stuff that wasn't actually useful. I didn't start from that perspective of what is something that I use all the time and I would like to keep using all the time. And so some things like that C and R notation, that was something I use. That's something I use all the time now because it's useful. It's a thing that I was spurred to do because I was sick of having to create input boxes that were exactly the right structure every time. And I was sick of having to generate matrices from scratch every time, and I wanted to have rand integer invertible. So I always knew I would have an invertible matrix whose inverse is also filled with integers. That's why I describe these as being best used as a reaction. If you find that there is something that you're doing all the time, put it somewhere central so that you can access it and other people can access it too. I think the shortcomings of this system are the fact that it is so crowdsourced. So as I say, I keep finding little bugs. Most of the time they occur because there is a use case for a function that I just had not thought of. And it would be nice if there were good systems in place to stress test some of these things. So possibly Zulip's a good place for me to do that. I actually don't use Zulip nearly as much as I should. But now if I was to start writing a new project, like if maybe I went in and tried to add some support for binary codes, I would probably go to Zulip and say, here is a thing I'm working on. Here is how to include it. If anyone wants to have a go, and see if they can use it and see if they have any feedback. I would probably do that, and it would be nice if there were good systems to do that, like channels in Zulip or something. And lastly, I think that as related to that previous point, standardization and documentation is difficult. I mean, if I'm going to go back to the eigen slide, eigenlib, notice that we have vector matrix, value matrix, vector matrix, value matrix, matrix value, matrix value. They swap the order of the inputs for these one set of functions, but these have been existed for 2 years now, so I can't go back and change it or it'll break all of the old questions. I wish I'd spotted that. That would have been really nice, but because I made these over a period of time, these things slip through the cracks. So same idea as before, I think. It would be nice to have some sort of more coordinated approach to that. And sort of more personal reflections. I actually really enjoyed this project. This was it was a really nice way of like I'm not a software developer. I studied mechanical engineering and I have an intimate knowledge of our first and second year engineering mathematics courses at UC, and that is my skill set. And so I find myself not very able to work on features of stack that are closer to the back end. This was a really nice way of being able to contribute in some way through creating useful stuff for people just in the way that I would normally write stat questions for myself. And so if people have specific skills within like mathematical topic skills, I would recommend this type of project because it was really satisfying, it was really interesting, and I hope that it is useful. Like I sort of keep seeing more comments from people saying that they have gotten good use out of this, and that's very nice to hear that. And I think that is the thank you on my last slide got deleted apparently because I used a template. So imagine this. Hang on, I can do this. Oh, it's red pen. That's not helpful. All right. I'll go back to a whiter slide so that we can see my face properly again. Oh, the thanks are still there. Great. Yeah, okay, George, that's a great comment. And counter issue with the cast time, it's a long compilation times. Yeah, so I did. I got a lot of that. Originally, the way that I did this was actually, I wonder if I can find it. I'll very, very briefly try and have a look for this. Oh my goodness, I didn't realize I drew on my screen. Can I erase this? Yeah, good. I did it all in one big hang on, this is going to be a little clumsy. One big stat question that had everything loaded in all the time, which was not a good way of doing this. Everything was very, very clumsy. I don't know where I would have put it. Do I have my name in here? Basically, my way around it in the end was to I just want to see if I can find this. Linear algebra version. Yeah, version 105. That sounds about right. So yeah, this was my working document that had all of my test cases, all of my functions, all in one spot. And this one was not usable by the end. Too much stuff. See if I can run the function. Oh no, okay. It's not working anymore. And then I eventually moved to GitHub so I could import things. But even then, I was still importing the whole lot, and so compilation would take a long time. It was very slow to use. That is one of the big reasons for this breaking them down into these smaller libraries. Is it was just unworkable by the end. So my solution to that, if I was to start it again, would be to begin with separate files and think very carefully about how to group things. As soon as something started getting unwieldy, I'd want to split it up. My main strategy for that was always I wonder if I've still got a clone of this. I have. It's been ages since I've used this. How do I remember? Don't remember how to use this one again. Branches. No, don't remember. I had my own branch. I was working and stuff here, and I was pulling from it directly. I could keep waffling on about that, but I won't. Does that answer your question, George? It's my answer is yes, and I did not handle it until I split it up into different pieces, which worked, but it feels a bit clumsy.
So thank you, Luke, again for this very interesting talk. And I
You're
think
very welcome.
yes, I
I'm glad
think
it
we
was
learned.
interesting. I hope
No,
that it didn't feel too much like I was like you were in a student lecture again, and being presented with a whole bunch of information that didn't seem relevant.
no. To be honest, it's very useful. I want to go back and watch the recordings because I became aware of these libraries like this semester since I started using a few of them, but not all of them. And
Mhm.
I think there were a few examples that you saw that I wasn't sure how to use them. That way I never used them. So
Mhm.
the seminar has been very useful. And well, I'll follow up with the next thing. Do you have any questions that you would like to share at the Stack library that contain some of these libraries?
Oh, I can certainly find some of them. I haven't prepared a specific list, or not that one. That's not
No,
one.
no, no. It's not
Um,
something that you need to do it like on the spot.
I think I contributed a few questions to the default installed library. So there will be some that you can access. I don't really use those ones. But there are certainly some in there. And I wonder if I can find any particularly good ones. go. Find bases for subspaces of a matrix. So this is one where I'm using vector spaces. This is one where I wrote it before I had my randomization function, so I've got my own bespoke things in here. But we can already see I'm immediately using row space, which doesn't exist. Otherwise, I'm using scale nicely. I'm applying C to these. I've got a custom validation function that this one's actually quite nice. I can show that here, where if a student malforms their input, maybe they just make this a tuple or something, they don't think about it, then it will tell them, no, your answer should be a set of column vectors, which saves a lot of headaches. And then down here when marking, my main marking code includes check that the student's answer is an equivalent subspace to my answer, and then check whether the student's answer is linearly independent. And so it makes this a bit simpler than it would otherwise have been. I'm very happy to share questions if people have specific requests as well. If they're like, I want to know how this function's used, then you can send me an email and I can send things through. Few sample questions to the stack question lib. Yeah, Juma, I think there are some. I'll need to remind myself how I get access to these. If I go, what do? You create a new question, and then question library. So this is a while since I've looked at it.
Yes, that was I was asking as well. Like, if you could share some examples, or you hadn't noticed that.
I think there are some that I added to. I don't remember where. I don't know how to get to them or where I would find them now. But I do think that when we published these contributed libraries, I included a few sample questions. So I might need to go looking for them. Topics probably, isn't it? Linear algebra.
Linear algebra probably would make sense.
Yeah. Vector spaces. Find bases for subspecies of matrices. So that like this is the one I was just looking at, or an older version of it perhaps. So I think there are some things in here. Give eigenvalue multiplicities if we have a look at this. Yeah, this is one of those ones where I use the geomult and algmult functions to generate the correct answer to these answer boxes here. So there are some things there. Hopefully there are interesting things. And again, if people want to see more of something, then they're welcome to email me and I can always add more into this. The only reason I've only added a few is because I didn't want to trawl through our question bank. We've got quite a lot of stuff.
Any more questions or comments from the audience? No, if not, probably we'll thank Luke again for staying up late to give this seminar.
That's quite all right.
Yes, maybe I should stop the recording. Stop recording.